good to see you. Welcome on in. Happy Thursday. We're going to have an easy day today. Easy day. We're going to go through the next part of our Pytorch tutorial journeys. We have this training model section, which is training with Pytorch. We're going to train an AI. And this is a convolutional neural network. Really easy. We've actually done this like 3 or 4 times already on stream. However, we're going to find out. We're going to find out if there's anything crazy or new that we're going to learn. There always usually is like 1 or 2 tidbits in there. So we're going to find out. Hey, Klogi, what are we training today? We're going to be doing a convolutional neural network. And I believe it's just some clothing pictures again. We've done this before. It's going to be an easy day. We're going to sit back. We're going to see if we run into anything that we haven't seen before. Apparently it's new in the tutorial. It's new. It's like really late in the tutorial. It's like second to last. And I believe we've covered all the tutorials at that point. I think we've covered everything. Can you walk us through the process of choosing the right layers and number of neurons? I think that's kind of hard to estimate. It is. What you want is the minimum. You want the absolute minimum that you can get in order to achieve good results. Because otherwise you're just throwing away data and compute. You're wasting compute. You can make the numbers really big and get really good results, but at a cost of very slow training and lots of compute waste. So, Soki, the answer is the minimum. You were seeking the minimum. You want it little. Seems like Safar. Well, so there are different kinds of layers because you've got projections or filters, and then you've got connected layers, where it is fully connected. And with transformers, you've got 3 filters, right? You've got query, key, and value, QKV. And convolutional neural networks, you have a dynamic number of filters. And you could have like hundreds of filters. And you want to do that for edge detection because you're going to do a max pool to find the highest value to detect the edges. Oh, the Saphir 10 problem. Oh, let me see here. Let me see. Is that an image problem? Let's look this up really quick. Oh, okay, yeah, okay. So that's just a bunch of pictures, and it's a classification problem. So you just do standard CNN. You're actually do what we're going to do today. You're going to do exactly what we're going to do today, and it's actually not that challenging. All right, you bring up a good point. All right, the Saphir 10 problem. It involves 60,000 images, 32 by 32 pixels, 10 distinct classes: airplane, automobile, bird, cat, dog. We're doing the same thing. We've got 10 classes, and we're going to do clothing items, so it's essentially the same thing. We're going to do that today, Soki. That's the plan for today. Meet you on Monday. Sounds good, Dreamer. Second like. Oh, the Dreamer, thank you. I see your message there. Tag in desktop gives you pooling's really easy. It's really easy. So I've got it around here somewhere. Here, I'm just doing this max pooling. Do I have it around here somewhere? There we go. Okay. So we've got a picture of a cat here. And then say we've got a bunch of numbers. See like these numbers here? We'll zoom in a little bit more. We got some numbers here. All right, check this out. So we'll do a max pooling where we focus on just capturing. So it's a window of 2, stride of 2. So here, we'll do a max pool over this. So you see we're looking at 4 numbers. And what the max pool 2-dimensional does, how's it going there? Shaya, welcome on in. Jefferson, hello. Good to see you. Welcome on in. Happy Thursday. All right, so okay, so this is max pool. Let me get this going here, number 8. Let me type 8 here. This will be max pool 2D. Really easy, okay? So that means that we're going to be looking at all of these values here, okay? And we're gonna look at 4 at a time, right? These 4, and they're all like next to each other in a 2D grid, right? In 2D grid, so there's proximity to each other. The max pool basically says, what's the max value? And then it takes that max value. So it basically divides the total resolution of the picture by 4, but it looks for the biggest value. That's it. That's all it does. Isn't that amazing? Isn't that crazy? We'll discuss specific loss functions when we use them. We'll take a look at the Pytorch optimizers, which implement algorithms to adjust the weights of the model based on the outcomes of the loss function. Yep, we know all about that. I think we're getting pretty good at this now. Finally, we'll put all those things together to see a full Pytorch training loop in action. End to end, everything is going to be covered. This is a full coverage into it. Datasets and dataloader classes encapsulate the process of pulling your data in from storage, which is usually a hard drive, right? Hard disk drive, solid state drive, exposing it to your training loop in batches, which is the nice thing. I do like that with dataloaders. They are very, very nice because they will shuffle your data because you want to randomize the data when you're training. And they will also pull in batches from that shuffle, which is nice because that's a lot of extra, work that you don't normally have to deal with. That's one, I think that's, and then the automatic transformations. There are, don't get me wrong, their unit of data probably in this case is going to be like one picture. So this is like a shoe, right? So this might count as one unit. Though if you're thinking of units, you're probably talking about a parameter or a weight or a coefficient, which is just a number. It's just a single number. What does that number look like? It looks like this right here. So you might have like a number, and that number is one of your parameters. It sure is. What is a unit of data? Like samples? Maybe like a megabyte? Exactly. It depends on your scope. What are you looking at? Can't we do a multi-process kind of approach? That's what we do. That's what we do. Look at all these numbers. There are too many numbers there. So we need to multi-process it. You got it. You got to multi-process it. Which we're going to do. We're going to do. We're going to be using GPU accelerators, you guys. Okay. So dataset is responsible for accessing and processing a single instance of data. That is going to be a picture in this case. One photograph. The data loader pulls in that instance automatically with the sample that you've defined. It collects them in batches and returns them for your training loop. The data loader works with all kinds of data sets. Doesn't matter what it is. It could be anything. So, let's see, AI.2 divide. Does this mutate? Let's try this. Full. That is... Let's try this. Do we have to mutate it? Yes, we do. Okay. So we have to shadow the data. Okay. So now you can see, I forgot what we were doing because I got all distracted, but we can, so you don't need to say .2 device, you just say .2 like this. It's a little function right there, and it automatically understands what you mean when you run 2. So you can move this over to your GPU accelerator. .2 does not mutate, it duplicates. Yep. Yeah, we just found that out. And always got to test it. For this tutorial, we'll be using the FashionMNIST dataset, an easy one. We use Torch Vision Normalize to center the zeros and normalize the distribution of the image content. So all the pixels. There's a lot of data in these images that we can sort of compress and reduce because many colors in these images don't even get used. So it's a giant color space, right? It's 256 or 255 times, 256 times 256. So it's a lot. It's a lot of color combinations. So we can delete most of them by normalizing. July 14th, 14 years. There you go, 14 years. It's a long time. Yep, vision transformers. Yep, there you go. Kind neat. We're having a CV this semester. Thank you guys for the reactions. It's kind of tough. Let's go through this tutorial, you guys. Let's start typing this stuff in. So we're going to do vision, torch vision with transforms, which just allows us to mutate the data into a shape that is going to prepare it for the input on our model, because we want to get those numbers between 0 and 1, right? Get those numbers between 0 and 1. Time, and we need summary writer. So from torch.utils, TensorBoard, utils.tensorboard, import summary writer. Import summary writer. Let's make sure this runs. Success, okay. And then we need from date time, import date time. We're going to be using that for later. Go back to our tutorial. So we're going to create a transform, compose, ToTensor, and a normalize. All right, transforms, compose, tensor, normalize. All right, let's try it out. Our training set and our validation set. Training set, and then our loaders. So we get our sets and our loaders. So let's do this. Torch Vision datasets, FashionMNIST. Training set. It's going to be Torch Vision dot datasets dot is it called FashionMNIST? Are we doing FashionMNIST? Oh yeah, we are. Okay. FashionMNIST. Which means higher level. The fact is simple. It doesn't change that. That's a good point. That is a good point. It's still functional. So yeah, occasionally functional programming is simpler. Sometimes it is. I like my lambdas. That's my favorite. My favorite right here. I like my lambdas. Kamala, it's good to hear your name coming out of my mouth. You have an excellent memory. It's good to see you again. It's good to see you. Let's see. What did we need? We need, what was in here? All right, so I guess, sure. Data, I guess, for the directory. Oh, that's where we're going to store it. Train equals true, and what, transform. Okay, we're going to pass in the download true. Okay. Transform equals transform. And the download equals true. Okay. I believe that takes care of that. This will be validation set. So this is training and testing. So train, this should be false. I think everything else is the same, right? Yeah. Okay. This is great, you guys. All right, so now we're gonna create our data loaders. Torch util data.dataloader. That's a lot of stuff to have to deal with there. Let's do training loader. Torch.utils.data.dataloader. Data loader. And we're gonna have the training set, I believe. Batch size and shuffle. Okay. Batch size equals 4 and shuffle true. Let me copy and paste this for our validation loader. Validation. And then we need this to be our validation set. The rest is the same. We don't need a shuffle though, false. I don't think we need to shuffle that, right? No shuffling on that? No shuffling? Yep, shuffle false. I knew it! When are you breaking out your data set utilization? Oh, okay, there it is. Well, not quite. Yeah, I mean, yeah. So this is, I believe it's like 20%. This is 80%. Oh, right here. 20%, 80% of the data. If that makes sense. If that's what you're asking for. Let's do print f string training set size. This will be len of training set. Training. There we go. And then validation set size. Let's see if that runs. Archive. Okay, so let's do some math on that. So total equals let's see, validation set plus total size, and then we want, let's say, here, then we can do division. We can do some division here. Thank for the hearts, you guys. Appreciate it. Thanks so much. Good to have you here. Let's keep going. We're coding now. We're coding. We're like deep into coding. All right, we're doing focus mode. When you like your YouTube live, there is a light bulb. Is there really? Loons, I have no idea. All right, you guys, focus mode, focus. Let's lock in. Let's see. And then that is, let's do a percent. We'll do percent len training size, and then we do, there we go, divided by total, right? And we do multiply that by 100. And we'll do the same for validation set here. We'll just like do a little quick, easy, a little smidgen easy. There we go. Looks good. There we go. We're going to do this part. All right, so we're going to write this function here. If one channel... do we need that? One channel true. If we're just assuming that it is going to be one channel, let's not even bother with the if statement. Okay. Def AMG show. So we're gonna display the picture. IMG, just IMG. That's it. And then we're gonna say unnormalize. Oh, that's neat. I didn't know you could do that. Look at that. That's like a really neat little trick right there. Okay. IMG equals IMG. Was it divided by 2 plus 0.5. Okay. And then this is weird though. It's weird. NP image. Okay. Let's see, yeah. img.num. Oh, to numpy. Oh, I see what's going on. Okay. img.numpy. So this is going to convert our tensor to a numpy into a numpy. NP img. Let's make sure this still works. Okay. All right. You have a 1 plus 9? Yes. Very good for spotting tiny details. You are, Loons. You figured it out. Very nice. You figured it out, Loons. So we're going to do... I don't want to grayscale it. I just want to show it regular. So plt.showImage. That's it? That's all we have to do? Look how, like, advanced this looks, and you don't need to do any of that. So this is going to be plt, one of those images. We're going to get a data loader, and we're going to grab a batch. Okay, data iter equals iter, and we're going to load in our data loader. There we go. We're going to say images, comma, labels equals next data iter. Data iter, please. Thank you. And then we're going to grab all those and then throw those into img show images. Is that it? Is that all we got to do? I think that's it. Oh, wait, no, we got to do one more thing. We got to do one more thing. So I'm going to try this. I'm going to say 0. And let's try running it. Okay, we got a problem here. We got a problem. Invalid shape. Is that because of our transform? No, it's because of this. Let's hide that for a second. Okay, invalid shape. What did it want? What is it looking for? What's it about IM show? It's just fine. We're gonna find out. We're gonna running it from a terminal window, right? And so we get the short stick. We get the short stick. Let's do a grid. Let's do a grid really quick. Torch utils make grid. So img grid equals torch utils dot. Is it torch vision? Yeah, torch vision. Torch vision utils make grid images, and then we should just be able to simply pass in images directly like this. Let's try that. I should be fine. Let's get through the model here. The model is really straightforward. We've done this multiple times. This will be our garment classifier, you guys. This will be a garment classifier. Okay. So we're going to say our, let's see, def. How do you spell garment? All right, let's make sure that we did this correctly. Nothing, no errors. Torch.nn, isn't that what we did? Yeah, torch.nn.module. right here. That seems fine. This is class. That's why. Okay. You think Gemini's nanobanana could make one? Yeah, it could. Yeah, it could. Yes, indeed. All right, so we're going to do a simple ConvNet 1, 2, and then some linear layers. And 165, 2x2 pool. And then so 6 filters, kernel size 5, 16 filters, kernel size 5. So let's do conv1, conv2. Okay. So we're going to say self.conv1 equals torch.nn.conv2d. Is that right? Yeah, conv2d. 1, comma, 6, comma 5. We'll do a conv2. And this will be a 16, 6. What is our same kernel size, right? Yeah. And we're going to do a pool. Self.pool equals torch.nn. We max pool. 2 dimensions. 2x2. Okay. So we've got multiple pools here. IBM doesn't have an official mascot. Their closest thing is the beef from designer Paul Rand's famous IBM. Oh, really? I didn't even know that. Where the B in IBM is represented as a bee, like a flying bee. They're better known simply as the nickname Big. Let's see here. I want 16. Okay, so 16 filters by 4 by 4. Okay, 16 filters. So this is 16 filters times 4, which I think are our channels. And then the output's going to be 120. So that's the output dimension. See, 2 and 3. So it'll be 120, 120. And this will be 120 and classes, which is going to be 10, right? There's 10 classes here. I suppose if we're gonna try to follow the tutorial this time. We're not gonna mess around with it too much. All right, so we've got all of our layers defined. Now let's run those through the forward pass. Out equals, see, conv1. Inputs. Return out. Okay. And then I want to test it here. All right, see, print, so see, out equals model. Then we're going to go images. Then we're going to say print out. Let's make sure that we did this right. We should see, that is correct. I believe this is correct. Let's do, see, torch. Well, what we could do is we can have an activator here. Self.gelu equals torch.nn.gel. See, how do you say that? Let's find out. Let's see what it actually is. Python, import torch, torch.nn. Let's see, dir. Here it is. Gel. Is it all caps like that? Where's the... So that's... Let's try this. Rel U, like that. See, I'll just call this. Let's call it gel. And then I want to say, self.gelu. Let's make sure this works. Okay. then we will test this out here. And it worked. That did the trick. That's ReLU. That's straight up ReLU. Okay, so I want GelU now. Can I just say GelU like that? Is that better? No, it doesn't like that. There isn't one. I guess it's with a capital E there. I'm good, thank you. C-E, all right. I saw that in the dir. And there we go. Okay, we're looking good now. All right, we're on the right track. We're on the right track. Okay. So then we're gonna do a pool. Do we activate first or do the pool first? No, we do the pool second. Self.pool. And there we go, perfect. Let's run that again. Are we looking good? I think so. Okay. Now, let's continue onward. So let's be out. We're going to the next convnet to, I think that's it right there. Easy. Yep, there we go. And then we need to do our linear layer, and we need to set a view on that. Self.linear1 L lin1 self dot see out, but we need to activate this as well, and this needs to be a dot view -1, and this needs to be, is it 16 by 4 by 4? I think something like that. But before we do this, let's get the shape so we understand what that looks like. Okay, so it is 16 by 4 by 4. Perfect. Okay. So we need to output that as a different view. I just want to see what the view looks like afterwards. So this should be a vector. This should be a vector now. Okay. So yes, it's a vector with a batch of 4. That is size 256. It's a 256 vector. Okay, perfect. So we got 4 vectors because it's the batch size, right? It's the batch size. And then I want, we're gonna linear output. Yep, there we go. There we go. And I think we need to do a self.GelU. 3, 3. And then the final output is going to just be a linear out, right? So now we should see, what we should see now is a 4 by 10 shape. That's what we should see. The output now should be, let's get our activations ready. We already have our dummy data. Oh, so this will do a quick little loss. Neat. Oh, that's kind of neat. You know, we don't need, we already have that. We don't even need that. So we already got our data here. We got our data. So let's grab our loss function equals torch dot, we're doing, no, cross entropy loss, right? And then we can test it. Loss equals loss function. Then we will go images. No. Out, comma, labels, like that. Print loss. See what that looks like. All right, there we go. The loss is 2.3, looking good. All right, that's a good start. That's a good start. So we are basically halfway through, which is very good. We're at halfway point. What we want to do is, I would say, all right, let's type up our optimizer really quick. And then this will put us in a good spot for tomorrow. Optim equals torch.optimize dot stochastic gradient descent. Then we say model dot param